So far, we have talked about the use of delta G to determine whether a process occurs spontaneously, not spontaneously, or reversibly. While this may be the principal use of delta G calculations, there is also another significant application of delta G that is concerned with predicting the maximum work that can be done by a system under reversible, isobaric, and isothermal conditions. To derive the relationship between work and delta G, we start with an expression of G as H minus Ts and replace H by U plus PV, so we get G equals U plus PV minus Ts. Then we write that we are dealing with a spontaneous isobaric and isothermal process, so we write delta G less than 0. We recall our introduction of spontaneous processes at the beginning of Chapter 2 with the statement that spontaneous processes are processes that can occur without work being done by the surrounding on the system. Since the process is spontaneous, we ask how much work can be done by the system on the surroundings as a result of the process. To calculate the work, we need to focus on changes between the initial and final states of the system. Using the above expression of G, we express delta G as the change in U plus PV minus Ts. This is equal to delta U plus the change in the product PV minus the change in the product Ts. We indicated that we were interested in isobaric and isothermal processes, so the change in PV is equal to P times delta V, and the change in Ts is equal to T times delta S. We also use the first law of thermodynamics and express delta U as the sum of W plus Q, and indicate that there will be two types of work: the traditional expansion compression work and some non-expansion work, that is, work such as electrical or mechanical work we hope the system can produce. Since U is a state function, we can choose any path we wish to calculate delta U. It is advantageous to use a reversible path to express delta U, as on such a path we can replace P external by P and equate Q with T times delta S, as per the second law of thermodynamics. Next, we substitute this expression of delta U in delta G and obtain delta G equal to minus P delta V plus maximum reversible non-expansion work plus T delta S plus P delta V minus T delta S, which simplifies as delta G equals maximum reversible non-expansion work. Since delta G must be negative, so must the work. So we've shown that under isothermal and isobaric conditions, a system undergoing a spontaneous process must produce some work of magnitude equal to that of the change in Gibbs energy during the process. The relationship between the change in the Gibbs energy and the work has many very practical applications. For example, consider redox chemical reactions. We know that when reduction half reactions are combined with appropriate oxidation half reactions, an electrical current can be generated. The equation we just derived will allow us to predict the electrical voltage, hence the electrical work that can be produced by a redox reaction. This has very important implications, for instance, in the industrial research on batteries and fuel cells. Reactions that give rise to the transfer of electrons are widespread in animals and plants. Examples include the oxidative breakdown of foods, photosynthesis, and nitrogen fixation by microorganisms. Electrical work is not solely associated with the transfer of electrons. The spontaneous transfer of ions across membranes also produces electrical work. In Chapter 5, for instance, we will talk about the active transport of protons across membranes. We close this lecture in Chapter 2 with a review slide concerned with the calculation of standard reaction Gibbs energy changes, delta RG standard. Two equivalent approaches can be used. First, in the same way we calculate standard reaction enthalpy changes, delta RH standard, from the standard formation enthalpy changes, delta FH standards, for the substance involved in the reaction, we can calculate delta RG standards from the standard formation free energy changes, delta FG standard, for the substance involved in the reaction, and from the appropriate stoichiometric coefficients. Delta FG standards are listed for a large number of compounds in the same table at the back of your book you use for standard formation enthalpies, delta FH standard, molar entropies, SM standard, and molar heat capacities, CPM standard. The second approach consists in using the relationship between G, H, T, and S for isothermal processes. That is, delta G equals delta H minus T delta S. For chemical reaction, this relationship becomes delta RG standard equals delta RH standard minus T delta RS standard, where delta RS standard is calculated from the stoichiometric coefficients in the reactions and the standard molar entropies of reactants and products. Both approaches will yield values of delta RG standard that should differ very little from each other.